You had your test sitting there. I just entered the grades. I must have left them in my office. I'll go back and get them. Give you guys something to work on towards the end. First of all, any questions on the 3.1 assignment? Everybody, which I know I didn't really have time to pull up in class. So yeah, here it is. Ask what's an experiment. Ask you to find the probability of certain things based on a given sample. Right? It gives you either a 1, 3, or 4. Then we have the probabilities for each. So you basically just have to sum those probabilities, right, for this problem. So it says A is either a 1, a 3, or a 4. And over here we have the probabilities of the 3 sample points. And of course, you go open it in StatCrunch as well. And you just basically sum each of the probabilities for the given sample point. Right, so pretty straightforward here. Here's our different marbles.
What is an easy way to figure that, or do you just need to sit there and write it out?
You just do it in a systematic approach, yeah. So you would start. It says 2 marbles are drawn at random without replacement. So basically I would start with B1, then go with B2. Kind of build a tree, which is a good way to think about it. So you would do B1 with B2, right? B1 with B2. Then you do B1 with B3. And then B1, is there a B4? Yeah, B4, and then red 1, red 2, and red 3. So B1, red 1, B1, red 2, and B1 with red 3.
Okay.
Then I would start over, draw a line, and go B2, right? And go B2 with B3, B3 with B4. And you don't have to include B1 anymore. And then after you do your B2 column, then start with B3. And you'll notice this tree will start to get smaller as you go, right? This is without replacement, and doubles don't matter. You've got to kind of read through and see which one. Notice this set's a little bit bigger than that set. So just glancing at it, it's probably C, but I haven't went through and done every single one. But that's the easiest way to do it, yeah. Start off this way, go with one element, and match it with all the other ones, and then you don't have to worry about B1 anymore, right? And then you go B2 with B3, B2 with B4, B2 with R1, R2, B2 with R3. All right. So then there's that. Then I would start another column with B3. See how it gets one less, right? Here we have 1, 2, 3, 4, 5, 6 combinations. Here there's 1, 2, 3, 4, 5. Next one will be 4, then 3, then 2, and then finally 1. All right? So that's the best way to go about it. For me, that's the easiest. You know, you can go B1, B2, B2, B3, go this way, but I like to just exhaust one of the marbles, then move on to the second one, and do all the pairs that way. It's kind of how I like to write it out. All right? So what we could do here, though, is determine how many pairs there should be. right? By doing our, what, 6, or there's 7 choose 2, right? Because there's 7 marbles, B1, B2, B3, B4, red 1, red 2, and red 3. So that's 7 marbles, and we're making a list of, or combinations of 2, right? So we could do, just to verify how many there should be, we could do 7 choose 2, right? Our combination formula that we learned yesterday. And then we could actually count how many there should be. So as I go through and do 7 choose 2, remember it's 7 factorial over 2 factorial, 7 minus 2 factorial. So this is equal to 7 factorial over 2 factorial, which is just 2, right? 2 times 1, times 5 factorial. I've dropped the factorial sign. I can add it in. It's the same thing. So here, this includes 7, so it's 7 times 6 times 5, right? 7 times 6 times 5 factorial over 2. I'll just go ahead and put 2 times 1 times 5 factorial. So right here, I can cancel out my 5 factorials. I know 2 goes into 6 3 times. I know I should have 21 combinations. There should be 21 pairs, right? 7 times 3 is 21 combinations. And if you go through and read this, right, it'd be 6 plus 5 plus 4 plus 3 plus 2 plus 1. Right? 6 plus 5 is 11, plus 4 is 15, plus 3 is 18, plus 2 is 20, plus 1 is 21. Same thing. Okay? So that's kind of a check. Your combination formula is a good check to make sure you have enough. Because as we look at part B, it doesn't have, see, it's got B4 with R1, R2, and R3, but it doesn't have any of the red marbles together. There's no R1 with R2 or R1 with R3. It's just got blue and red together. It also doesn't have any of the blues with blues in part B, right? It's just blues with reds. So it's missing a lot here. And I can't make this any bigger, even if I zoom it in. Look, it zooms in the text, but it doesn't zoom in the actual problem. So I can hit this button, which actually makes it smaller. All right? A cyberchondriac is a person who regularly searches the web for health information. Which sometimes that's more scary than what you already have, right? You go to like WebMD and it like pushes you off to the worst possible thing for your symptoms. Could just be a headache and it says you have some virus or something. Okay, so we are going to use, we're going to piggyback on this probability stuff for the next section. I went ahead and set up everything up to the next test. Right? So what I've done is I've included this 3.5 and 3.6. Some stats teachers don't cover it. I'm going to go ahead and cover it together. I'm not going to cover everything from both of those sections, but I want to cover some of it, especially the conditional probability. So I have, notice those 3 sections are going to take me a whole day each one, because they're all pretty long, right? But those 3 assignments, which definitely involve more than 3 sections, we've just kind of put some stuff together. And then notice when your exam will be. Exam 2 review is due next Thursday at 9 a.m. All right, so that's your next test. It's a week from Thursday. All right? And then the next Wednesday, we'll review for the test, just like we did for the previous one. And the Tuesday before, I'm only covering one section, so we might have some free time then to go maybe in the computer lab or ask questions about some previous assignments. So we don't have to rush through this part. All right? So let's get in and start with section 3.2. So jump down to Multimedia Library, chapter 3, 3.2. For you guys that have taken 106, you will see this stuff before. Or if you've taken stats in the past. Okay. So these are problems from 3.1, and then down here we start off section 3.2. Right, we're going to deal with two special things. One's called a union, the other's called an intersection. Right? And what this is what if one thing and another thing happened? Or what if one thing or another thing happened? That's the way we think about these events. They're called compound events. All right? An event can often be viewed as a composition of two or more other events. Such events, which are called compound events, can be formed in two ways. And the next page has a picture that really helps show what this is. Right? So, the union of two events, A and B, is the event that occurs if either A or B or both. All right? So in mathematics, when we say or, that could include both still. One or the other or both. All right? So the way we pronounce it is A union B. All right? Occurs on a single performance of the experiment. We denote the union of events A and B by the symbol A union B. So the U makes it easy to remember. It's a union. I mean, it's shaped like a U. All right? A union B. And I'll give you a little trick for how I remember it means or. So, A union B is equal to A or B or both. And I'll go ahead and put both in parentheses. So if it occurs in both, it's still in the union. The way I remember or, the way I remember that the union means or, is notice this U kind of has two things on top. One would fit in R, O, one would fit in R. If it's two letters, it's or. A or B. And I know this is kind of abstract right now. On the next page, we'll see some pictures. But right now, I just want you to understand that union means or. And then finally, we have an intersection of two events that occurs if both A and B occur on a single performance. So the intersection includes the union. Right? If it happens in both, it still happens in one or the other. Right? Because the union says or both. So the union includes the intersection. Right? An intersection is just like an intersection of two streets. Right? When you get to a four-way stop, that intersection is one street and the other street. Right? So A, let me write it like a regular A. A intersect B is equal to A and B. It has to happen in both. The way I remember and for intersection is, first of all, you can kind of draw an A right here in the intersection, or a line, and it kind of looks like an A. But the way I remember it is just to write and across the top. The word and fits. And that's just a little convention that I use that helps me remember A or B or A and B. So the union means or, the intersection means and. Right? We write A intersect B for the intersection of A and B. A intersect B, the way this is pronounced is A intersect B, consists of all the sample points belonging to both A and B. So union means or, A or B, or both, or means both. Let's look at the next page and see some pictures of it, which makes it a little bit simpler. So here's a Venn diagram for the union and the intersection. Entire shaded area So the A and B is shaded, even though you can't see it here. Let me rewrite it a little bit prettier. So here's our Venn diagram. Here's a sample event A, and here's an event B. So A union B includes everything. All right? This is A union B. The shaded area is A union B. So it's either in A or in B, or there is this little piece right here that's in both. Does everybody see that? A intersect B is only that little piece that's in both. We have a circle that means A, event A, a circle that means event B. Does everybody see the difference between those two things? The union means one or the other or both. All right? So you'll notice that the union includes the intersection. The intersection is what is in common to both of them. There's really a bunch of neat things online that really help explain this. So let me just type in Venn diagram. I'll just put Venn diagrams and Google it. So look at all this different stuff, and some of them are a little more in-depth than we need. I don't know what Betsy's Family is. That must be some TV show. Here we go. This is a good one. So we have an event called whales and we have an event called fish. Everybody does realize that a whale is not a fish, right? A whale is a mammal. But whales and fish still have things in common. They both live in water, they both have fins, and they both can swim. So if I asked you what's the intersection of whales and fish, it would just be that they live in water, they have fins, and they can swim. This really is doesn't have really anything to do with math, or statistics, even though it is a Venn diagram, right? It's just a way of grouping information together. So notice this thing for fish, the stuff with fish that doesn't have anything in common with whales is that they lay eggs, have scales, and breathe water. And then they turn the water into oxygen, right? Whales don't breathe water. They don't have gills. Right? They actually have to come up to the surface. They have hair, they give live birth, and they breathe air. That's really what makes them a mammal, right? So this is a good example of stuff that's in common. So if I asked A or B, the union would be everything listed here. All right? And I could even put the word can walk. Maybe I could put can walk out here, because that's not in common to either one. Even though there is a new fish they found down around Australia that can walk. Can actually survive out of water for like 8 days or something like that. So, but in general, I could say can walk. That's not common to either one. That wouldn't be in the union nor the intersection. All right, so here's a nice example. It doesn't have anything to do with probability or numbers. It's just actually a life example of it. And just on this page, where I just typed in Venn diagrams, I mean, there's thousands and thousands and thousands of examples. See this? So you can even do a 3-bubble Venn diagram. So Sam, this kid Sam, is blonde, is a boy, and is older than 8 years old. He's the only one that's common to all 3 bubbles. Now, we're not going to see a 3-bubble Venn diagram, but it's something that could happen. So Ian is older than 8 and is a boy, but does not have blonde hair, so that's why he's over here. Becky is not in any of the 3 bubbles, because she doesn't have blonde hair, is younger than 8, and is not a boy. Does everybody see kind of what's going on here? And I know in 106 there was a couple challenge problems where we had you build a 3-bubble Venn diagram. It was like, it talked about instruments was one of them, guitar, cello, or piano, I think. And if somebody could play all 3, they went right here. Notice this little triangle looking piece is the intersection of all 3 of the bubbles. Okay? So that's kind of an explanation of what in common and not. You know, this would be a pretty good way to study for other tests, for other classes. You know, kind of put what's in common, what's not in common. This association is really how we learn different things. Just like the or and the and I showed you. The way I write or and and on the union and the intersection. No, I wouldn't know anything about this. This is an animal and cell. Animal and plant cell. Both animals and plants have DNA, they have ribosomes, cytoplasm. But plant cells have cell walls where animal cells don't. Apparently. I mean, I would know if this is true or not. Yeah, I know chloroplast is something that makes them, gives them their color, right? But just a bunch of interesting things that talks about it. Moths and butterflies. How are they different? How are they the same? Well, the way they're the same is they each have 6 legs, they each have 2 wings, and they both do a metamorphosis. Right? Caterpillars come from butterflies, moth comes from another type of crawling insect that turns into a moth. As we all know, right? Last month we've had to deal with moths a lot. All right. Butterflies fly during the daytime, moths are nocturnal. That's a difference. That's not something they have in common. All right. Okay. So we have a good idea of what the union and the intersection is. Let's look at an example to wrap our mind around it a little bit more. Let's just do. Let's look at this applet and see. I haven't opened one of these in class yet on this computer. And of course it blocks it, so there we go. My office computer doesn't because I don't have the same settings. But I can't go in and change the settings unless you are an administrator, so we'll just leave it as it is. So let's look at an example and see if we can do this union and intersection. Let's do it without looking at the solution. Let's see if we can answer this. Consider a die-toss experiment in which the following events are defined. Toss an even number is event A. All right, so we're rolling a 6-sided die. So let's draw up a Venn diagram. And rather than put a dot and the number, I'm just going to put the number, all right, instead of putting a dot and the number. So 6-sided die, what are my 6 outcomes? Right. So I'm going to go ahead and call that S. So my sample space S is equal to 1, 2, 3, 4, 5, 6. Those are all possible outcomes of my experiment. So I could draw it this way in sample set notation, or I can use a Venn diagram. 2 ways to do the same thing. So I'm going to go ahead and define event A as an even number. So I'm going to draw a circle. I'm going to call it A. And inside that circle, I'm going to write all 3 of the numbers that are even. So we have 2, and I kind of know what's going to come next. That's why I'm going to write 2 right there. 2, 4, and 6. Does everybody agree that's event A? Toss an even number? All right. Event B says toss a number less than or equal to 3. So 2 is definitely less than 3, right? Does everybody agree with that? What numbers? This is number, or it's on page 124. Let me zoom it in one more time. Okay. So toss an even number, toss a number less than or equal to 3. So I'm going to go ahead and write event B, but I'm going to include 2 in event B because it follows it follows this rule of being a number less than or equal to 3. But what other things need to be in event B?
1 and 3.
1 and 3. But 1 and 3 are not going to be in A, right? Because they're not even numbers. You notice there is a number that's neither in event A or event B. What number is it?
5.
5. Let me write A. Here, let me change the color of this just so I can differentiate. A and B are not a member of the sample set. That's just what I'm naming these bubbles. I'm calling that event A and I'm calling that event B. All right? Everybody following along? Kind of see how I'm building this? Notice how the number 2 is common to both events. It's even and it's less than or equal to 3. So A says describe A union B. So let's write it in set notation. What are the numbers that are in A union B? So what is the set A union B? How is it different than S?
How is it different than S?
Yeah, what's different in A union B? What's not in A union B that's in S?
5.
5. So our set A union B would be 1, 2, 3, 4, skip 5, and write 6. So that's the answer to part A. The answer to part B is A intersect B. And what would be in that set?
2.
Just the number 2. Then let's do part C. So what's the probability of A union B? It's very important that they put this statement right here. It's assuming that the die is fair. So what's the probability of rolling any of the 1 numbers? Well, 5 out of 6 will be the answer to A union B, right? But to roll any of the 1 numbers is 1/6. So it's 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6. All right, 1/6 plus 1/6. Which equals 5 out of 6. So what's A intersect B going to be? 1/6. So another way to say that is, what are the chances that I roll a number that is included in A union B? Well, 5 of the 6 numbers on the die are included in A union B. So that's all 5 of the probabilities added together. And I know it's 1/6 from previous sections. If this wouldn't have been here and said, you know, assume it's not fair, there's no way that I could have come up with these probabilities without more information. I know the probabilities are 1/6 because it's a fair die. Okay? See that? Let me turn the light on so we can see that a little bit better. These markers are finally running out of juice. So here's our sample space. It involves the events A and B. What A and B have in common is the number 2. 5 is not in common to either A or B. So if you were in a casino and playing this game, and it said roll a die and bet whether you will hit A union B, you would bet on that all day, right? 5 out of 6. That's something that's very likely to happen. You wouldn't bet on this, but this would probably pay you 10 to 1 or something like that, right? The odds would be a lot better. That's how they change the odds, which we're not really talking about odds, just a way to kind of think about these experiments. So the probability of A union B is 5/6. The probability of A intersect B is 1/6. I know the probability of rolling one side of the die is 1/6 because the die is fair. Each of these events are equally likely. That's what fair means, right? each of those outcomes are equally likely. Okay? Feeling all right about this? I know this is the first time we've done this type of thing. We don't talk about probabilities at all in Math 106. So this is new. But the nice thing about the book is it really goes through and explains the solutions to the examples. It really makes it nice. It's a little dark. All right? So here's the union. A union B is the set of all numbers except 5. A intersect B is only the number 2. These two things are the same way, are different ways to say the same thing. All right? I prefer Venn diagrams because they're more visual than this set notation. Right? This is like a graph, right? Most people are better at reading graphs. It's just easier to see. And then here's our probability. So the probability of getting a 1 is 1/6, of a 2 is 1/6. I add together all the probabilities and we get 5/6. Which is what as a percentage? 83%. So you have an 83% chance of rolling a number that is included in A union B. You have an 83% chance of the event A union B happening. It's pretty likely. All right? And as far as the event A intersect B, it's not very likely, right? It's about 17%, which is a pretty low number. Okay? And this is very important. Look back. Since the 6 sample points are equally likely, that's very important. If we didn't know that, we couldn't really do this problem. They would have to give us the probabilities. All right? There's really no other way we could come up with them. Okay? And the probabilities in part C are simply the number of sample points in the event of interest divided by 6. Unions intersections can be defined for more than 2 events. We've already looked at a 3 bubble just from in my examples. For example, the event A union B union C. Remember that was the one kid that was older than A, was a boy and had blue eyes, right? He was in common to all 3 events. Now when you get to these 3 bubble, it's a little tougher to come up with, all right? But it's still something that's doable. It just adds one more layer of tediousness, right? None of this stuff is that difficult. It's just a lot of small steps, right? A lot of little things along the way. Okay, let's look at another one. Finding probabilities from a two-way table. Mother's race versus maternal age. So, based on the race of the mother and the age of the mother, does that have an influence on the baby? Right? So let's see what it says. Reported on a study of over 200,000 births in New Jersey over a recent 2-year period. That's a pretty big sample size, right? That's actually, we're going to call the population because that's every birth in New Jersey over a 2-year period. So it's giving us information about the population, right? We're going to see about the sample. We're going to try to create a sample from the population, right? The opposite of what we've been doing on the previous test. Previous test, we came up with the sample and see if we could infer about the population. Remember, probability is backwards from that. The study investigated the link between the mother's race and the age at which she gave birth. So how old was she when she gave birth? Because pregnancy lasts 9 months, so they probably changed age at some point in the pregnancy. Right? It would be probable that they did change age rather than they didn't. Right? Does that make sense? Because it's 9 months long, which is over half a year. Okay. The percentages of the total number of births in New Jersey by the maternal age and race classification are given. Right? So this is percentage of all birth mothers. So does this, first let's ask, what does all the probabilities have to add to in a probability experiment? 1 or 100%. Does this add to 100%? Let's just look at it. Let's add all these numbers together. 2 plus 3 plus what you could do in your head as well. Plus 33 plus 2 plus 2 plus 12 plus 5. Did I miss something here? Is it 74 and 5, 79, 83, and 17? Yeah, that's 100%. This calculator, I hit the wrong button. So 5 plus 41 plus 33 plus 4 plus 12 plus 5. 100%. Okay, so that's good. So all of our birth mothers in New Jersey have been given here. This table is called a two-way table since responses are classified according to two variables. But there's a lot of stuff going on. There's a lot of information put in here. Right? So, A, define the following event. A New Jersey birth mother is white. So that's the definition. So what would we do here? We'd add together everything here, right? So what's the probability of A? That's the next question. So let's read them and answer these three questions. All right. So A means a New Jersey birth mother is white. B is a New Jersey mother was a teenager when giving birth. All right? This isn't something we can really put in a Venn diagram. There's just a little too much information here. And we'd have to have a lot of different bubbles. All right? So let's find each of the probabilities first of each of the events. So little a says the probability of A occurring. What are the chances that the events in A occur? What are the chances that the events in B occur? So what's the probability of A? How would I come up with that? What are the chances that a New Jersey birth mother is white? You'd add the column, right? So you'd add 0.02 or 2%, and I'll go ahead and stay with the percent notation. 2% plus 3%, not comma, plus 3% plus 41% plus 33%. And what does that equal? Let me make a little 79%. So the chances of event A happening is 79%, which is pretty likely. All right. Event B, probability of event B. What am I going to add together there? How do we define teenager? Right? If the year, right, if their age ends in the word teen, right? 13, 14, 15. So what columns am I adding together? Rows or columns, or both? The first two rows, right? So I'm adding 2% plus 2% plus 3% plus 2%. %. Now part B, the intersection isn't very hard. The union we have to think about though. So we're going to find the probability of one or the other happening, or the probability of both happening. Right? So let's talk about the intersection first. What's the probability that a New Jersey mother is white and a teenager? What do I add together there?
3 and 2.
2 and 3, right? 3 and 2. So 2% plus 3%, which means there's a 5% chance that a randomly selected mother is a white teenager. That's what this is saying. What about A union B? Can I just add these two numbers together? Can I? Is it 88%? Right, because I'm counting the white teenagers twice. Because if this was true, A union B, then it would mean that black mothers that aren't teenagers should be the rest of it, right? Should give us the rest of our 100%. But what's the percentage of being black and not a teenager? That'd be 12% plus 5%, which would be 17%. If I add 17% and 88%, that's more than 100. We've counted something twice. And what we've counted twice is the white teenage mothers. So actually, to answer A union B, we would say, what are the mothers that are white or a teenager? So that would be these four numbers plus 2% plus 2%. Everybody see what's going on there? We can't count the 2% and 3% twice, which is what would happen if we just added together PA and PB. We would be counting these two values twice, which will actually come up with a systematic way to put together the union, and it'll take away that double, all right? So the answer to A union B would be basically PA plus PB, but minus these guys, right? We have to take away this double, because we've already counted it. We count it here, it appears here, and it appears here. So we only need to count that once. Where if I just added this plus this, we'd be counting that 5% twice. That's where our issue is, right? So the probability of A union B would be 2% plus 3% plus 41 plus 33 plus 2% plus 2%. And what do we get there? You get 83, right? Which it is not coincidence that the answer to the union is PA plus PB minus the intersection. Because in A and B, we're counting the same thing twice, so we need to take it away once. This 5% and that 5% has been included, which I could actually underline this one, just to make it easier. Right? And I know this is the first time we've kind of seen this stuff. It takes a little while to wrap your mind all the way around it. But after you see it a few times, it really starts to make sense. Right? So let's go in and look at the solutions from the book. Okay. So here's the different events. So they said event 1 is less than 17 in white. Event 2 is 18 or 19 in white. Event 3 is 20s in white, and event 4 is over 30s in white. And then E5, E6, E7, and E8. So they basically defined all 8 of those events. They've attached a number with a subscript to each of these 8 percentages. You see what's going on there? So they call E1 being white and less than 17 years, less than or equal to 17 years old. So then they go ahead and attach the percentages as relative frequencies. But notice I write the percentages, which is fine, but you have to make sure you write the percentage symbol. That's why I wrote the percentage symbol every single time. Because percent means divided by 100. Writing 2% is exactly the same as writing 0.02. Right? They are equal. They're always equal. That's why I didn't just write 2 here, because that would not be the same. I wrote 2%. Okay? So whether you write it as a proportion or a percentage, it doesn't really matter, all right? But if you do write it as a percentage, you have to include the percent symbol. All right? So they go through a fancy way of renaming this stuff. That's not totally necessary. But they come up with it the exact same way. Look, 0.79, I had 79%. Probability of B was 0.09 or 9%. And then the union of the events is E1, E2, E3, E4, E5, and E6. All right? And the intersection is just E1 and E2. Okay? Now, what if I asked you, remember this question was, they're white and a teenager. What if I said not white or a teenager?
White or?
Right, not white or teenager.
So,
Or not white and a teenager. So, basically, what would be the opposite of this? What probability? So what are the chances that they're neither a teenager nor they're white? Right? So one or the other. Which would be the opposite of this. But there's a special word for opposite in statistics. Right? It's basically what completes that value to make it 100 or to make it 1, right? To make it 100% or to make it 1. I need to add 0.95 to this to make it complete. Right? If I went in and counted up all the other events that aren't being white or a teenager, or white and a teenager, excuse me, that would be this one, because they're not a teenager, and all four of these, they're not white. So if I added together all of those, that would be the opposite of A intersect B. Does everybody kind of see that? Opposite? There's a special word for opposite in stats, and it is complement. All right, so let's talk about complementary events. A very useful concept in the calculation of event probabilities is the notion of complementary events. You know, and this really has the same meaning as, you know, when you go and sit down in a nice restaurant, like, and they have a dinner choice, and underneath they'll say kind of what wine would complement it, right? What would complete the meal. It's kind of the same type of thing. What makes it whole? So complement actually comes from the word complete. Right? The complement of an event A is the event that A does not occur. So another way to think about complement is not A. So A plus not A is 1. Okay? So here, if I let event A be, the mother be white, the complement to A would be the mother was black. Everybody kind of see that? It's the opposite. And we'll see some examples of this that are a little simpler than that mother problem. So the complement of event A is the event that A does not occur, or not A. That is the event consisting of all sample points that are not in the event A. We denote the complement of A by AC. See how it's got a little C kind of as an exponent? So that's what we're going to use in this book. In 106, you had learned a symbol that was called a tilde, kind of a squiggly line that came in front of it. That means the same thing as complement. An event A is a collection of sample points, and the sample points included in A complement are those not in A. Right? if AC are not those, figure 3.9 demonstrates this idea. Note from the figure that all sample points in S are included in either A or AC, or a complement. You know, you might hear me say AC. And no sample points can be in both A and its complement, which makes sense, right? Nothing can be both in A and not in A. That's impossible. That's being in two places at once. If you figure out how to do that, you'll be a millionaire, right? Because nobody can ever do that. This leads us to conclude that the probabilities of an event and its complement must sum to 1. The probability of A plus the probability of A complement always equals 1. It doesn't even matter what A is. Notice how I didn't define A, because it doesn't matter what A is. When you add together A plus its complement, it is always equal to 1. So the probability that something happens plus the probability that it doesn't happen is 1. The probability, or the chances that it rains plus the chances that it doesn't rain would always be 100%. It's a way to think about it. Very important rule right here. Right? So complement means opposite. That's a way to think about complement. It either happens. If it doesn't happen, then it's the complement. Oh, I skipped something. That's listed down here at the bottom of the page. There we go. So here's a Venn diagram of A. So A are the dots that occur inside of it. A complement are all these dots that are not in A. Notice when I add together A and A complement, I get the universe, right? I get my entire sample space. So there's that rule. The sum of the probabilities of complementary events always equals 1. They didn't even have to define what A was. It doesn't even matter what A is. Event A. Right? Because the probability of it happening plus the probability of it not happening is always 100%. Okay? Pretty simple concept on the top, right on the surface, but it really helps us throughout this chapter when we're coming up with probabilities. This is a very important thing. Okay? In many probability problems, calculating the probability of the complement of interest sometimes is easier than calculating the probability of the event itself. It's kind of like that, the mothers and the race problem. You know, A union B was kind of big, right? It involved 5 or 6 different probabilities. Finding its complement would have been easier because then we would only had to add together 2 numbers. So sometimes finding the complement is easier than just doing it itself. Notice here, if I subtract the probability of A complement from both sides, I can create this. So I just take it away from 1. Right? So find the chances that it doesn't happen and subtract that from 1. Okay, let's see if we can answer this one. Consider the experiment of tossing fair coins. I assume this is 2 coins. Yeah, 2, okay. So we are tossing 2 coins here. Define the following event. A, observing at least 1 head. So first let's find our sample space. How many different events are there going to be in S? So let's define S first. So S equals what? What are all my possible outcomes when I toss 2 fair coins? Now we have to think about this, whether it matters whether they repeat or not. Right? And in this case, it does matter, all right? So we'll consider them different events. And the way the book, yeah. So we have 4 things that can happen, right? This is where we could build a tree. So first we toss the coin. We have one of 2 outcomes. We can either get a head or we can get a tail. Then from the second coin, we would either get a head or a tail, or a head or a tail. And really, I could do this again. I could do it for 3 coins, or 3 tosses. I just put head, tail at the end of this. All right? So we have the event head, head, the event head, tail, the event tail, head, and the event tail, tail. So we have 4 events here. We've kind of already seen this example once. So S is observing 2 heads, observing a head and then a tail, observing a tail and then a head, and then observing 2 tails. That's all of my possible outcomes. Now we are assuming that these, oh no, we're not even assuming, it's told us. The coins are fair, right? Which means they're 50-50. So what's the probability of each of these events if they're all equally likely? 0.25 for each one. 1 out of 4. All right? So let's find part A. Or A, now let's define A and then find little a. So A is defined as at least 1 head is observed. So that means we could get 2 heads and it still falls in A. Right? So in event A, we have head, head, we have head, tail, we have tail, head. So the only sample point that's not in A is when we roll 2 tails, flip 2 tails, right? That makes sense? So S is all possible outcomes. A is one specific event of outcomes, right? That's how it was defined. So let's find little a. Find the probability of A happening if 2 coins are tossed. Right? So A is probability of A is equal to the probability of each of the events in A happening, which you guys already told me was 0.25. So that's 1 out of 4, 1 out of 4, plus, which is equal to 3/4, which is equal to 0.75, which is the same thing as 75% chance. So there's a 75% chance that event A will happen, that we will observe at least 1 head when we toss 2 coins. Which is really pretty interesting if you think about it. Okay? All right, this next one I'm just going to kind of go over, kind of talking about it because it's a little more in depth, and the book doesn't even spend that much time talking about it. But you guys all get part A, that's how we come up with the probability if 2 coins are tossed. Now if 10 coins are tossed, imagine how many events there are. How many different ways can that happen? Well, we'd have to do 10 choose 2. We'd have to do our combination formula, 10 choose 2. So let's just do that, just to see how many different coins we can get. So let's do 10 choose 2. This is going to help us for part B. Now each of the events in part B are all equally likely. So 10 choose 2 is going to be 10 factorial over 2 factorial times 8 factorial, right? 10 minus 2. And this is equal to 10 times 9 times 8 factorial over 2 factorial is just 2 times 8 factorial. 10, no wait, that's not 10 choose 2. Hold on. No, that's how many different combinations can we do 10 from 2. That's not exactly what it's talking about here. So this isn't correct for this problem. I just threw it up here. It's actually the way you would do it. Let's go ahead and finish it out though, since I have it written. That's not how you do this problem, but this is good practice. 45, right? So there's 45 different ways to choose 2 from 10 things. But this problem isn't really asking for that. The way we would come up with the number of ways that we could flip 10 coins would actually be 2 to the 10th power. 2 to the 10th power. Define the experiment, list the sample points. So to do it from 10 tosses, we'd have to do this tree for 10 levels. This is 2 levels. We'd have to do it for 8 more levels. And then count up each of the arms of the tree. There would actually be 1,024 different ways that it could happen. Right? Which is equal to a gig in computer architecture. So the chances of getting any one of these events would be 1 out of 1,024, since they're all equally likely. Now you can see why I'm just kind of glancing over this. They don't even do it in the book. Right? But the way to answer that question, remember, A says observing at least one head. Right? Isn't that what A is defined as? So if I toss 10 coins, there's actually only one event that happens where I do not observe a head. That's where I get 10 tails. Which would only happen one time. That would just be this very right-hand side of my tree. Because no matter what path, what other path I would take, I would eventually hit a head. You see what's going on there? So this is a case where it's easier to actually find the complement than it is to find the probability itself. So the chances of not observing a head flipping a coin 10 times is 1 out of 1,024. Which is a very, very small number. See how the complement is no heads are observed in 10 tosses? Because A was defined as at least one head. A complement only has 1 point in it. Right? So this is not 10 choose 2. Ignore that I had went over. All right? So your chances of observing at least one head in 10 tosses would be what? What do you guys think? Right? Exactly. The probability of A in that case would be 1023 over 1024. Because there's only one event where you don't observe a head. So the chances of flipping 10 tails in a row is very, very, very slim. All right? Which it's actually 1/2 times 1/2 times 1/2. Right? Because your chances of flipping a tail in one event is 50%, right? So your chance of doing it twice is 1/2 times 1/2. Chance of doing it 3 times is 1/2 times 1/2 times 1/2, all the way out to 10. So it's actually 1 over 2 to the 10, which is exactly what this is. And you'll notice that the complement to this, the complement to A in this case, would be flipping 2 tails, right? And the probability of that would be 0.25. which is the same thing as 1/2 times 1/2. That's 1/4. And we'll actually get into talking about, as long as we know one event doesn't have anything to do with the other one, right? If I flip a coin once, the next time I flip the coin, what happened previously has no bearing on what happens the next time. Right? You guys agree with that? So what we'll do is we'll actually multiply probabilities together. Right? So we could even go and say, what's our chances of flipping the ace of spades one time? If I know the deck has been shuffled good, what are my chances? How many cards are there in a deck? 52. So you have a 1 out of 52 chance of getting the ace of spades, right? Does everybody agree with that, as long as the deck's been shuffled? So what's my chances of flipping the ace of spades twice in a row, as long as the deck has been shuffled each time? It's actually 1 out of 52 times 1 out of 52. So your probability starts going way, way down for getting 2 ace of spades in a row. Right? And that's how they come up with those chances of winning numbers that are on TV, is using this exact same method. Right? Oh, and then here you go. This answers my next question. Now use the relationship of complementary events to find probability of observing at least one head in 10 flips. It's pretty probable. 99.9% chance. You would never bet against not observing a head in 10 flips. Ever. Okay? I mean, you could probably flip a coin 10 times in a row for the rest of your life and never get 10 tails. All 10 times. It'll almost never happen. If it does happen, that's extremely lucky. Okay? So this one is a little more difficult. Right? We hadn't even really talked about that 2 to the 10th. You wouldn't really know how to come up with that yet. The book kind of gave it to us. Okay? That's why I kind of just glossed over it. So the thing I want you to get out of this section is this relationship right here. The probability of an event happening plus the probability of it not happening is always 1. Okay? Because that's all that can happen. It can either happen or it can't happen. That's it. There's no in between. There's no gray area. All right? It either rains or it doesn't. I mean, if you fill one raindrop, it's raining. Okay? Okay. So, what I want you to get out of this is these 2 rules right here. Very important from this section. This part B was kind of a tough example, all right? It really went in depth there. But you could have looked at that and said, it's pretty likely that if I toss a coin 10 times, I'm going to observe at least one head. That's pretty likely. Okay. Last thing for today, we're going to talk about something called mutually exclusive. Mutually exclusive means nothing in common. If 2 things have nothing in common, they're mutually exclusive. An event and its complement are mutually exclusive. All right? Mutually exclusive means nothing in common. In section 3.2, we saw how to determine which sample points are contained in a union of 2 sets. So that's or, right? That's one or the other. And how to calculate the probability of the union by summing the separate probabilities of the sample points. It is also possible to obtain the probability of the union of 2 events by using the additive rule of probability. What the additive rule of probability does is basically adds together the chances of both of them happening and then takes away the intersection, because we count the intersection twice, just like we did in that mother's problem. Right? How we were counting the white teenage mothers twice if we would add together A and B, because that's what they had in common. So let's look at this picture over here. The entire shaded area is A union B. The middle right here is the intersection, right? That's A intersect B. So if I wanted to find the union, I would add the chances of A happening plus the chances of B happening, but then I've counted this section twice. So I need to take it away once. Does that make sense? So it's really kind of like adding together A plus this crescent portion of B. Is kind of a way to think about it. All right? Well, actually, that's not a crescent. That would be called a gibbous in that case. Right? So the additive rule of probability. The probability of the union of events A and B is the sum of A and B minus the probability of the intersection. Because this intersection has been counted here and here, so we need to take it away once. Right? It's like if I had these two mouse pads. Right? If I did them in a union, where they had a little bit of an intersection where they overlap, and I wanted to count the probability of the union, I would add the surface area of this mouse pad plus the surface area of that mouse pad, but then I've counted this surface area that's overlapped twice, so I need to take it away once. All right? That's essentially what's going on here with the additive rule of probability. It's like saying, what's the surface area of this mouse pad now? Well, it's this surface area plus that surface area minus the overlap, because that's been counted twice. Okay? That's why we only subtract it once, because I still want to take it into account one time, but I don't want to count it twice. Okay? Very important rule. So the two rules we really want to get out of this are probability of A plus its complement is 1, and the probability of A union B is equal to the probability of A plus the probability of B minus the probability of the intersection. We will use these rules a lot in this homework assignment. And these you'll be given on your formula sheet for the test. Right? You won't have to memorize that stuff. So our rule of complements and our additive rule of probability. Notice if I've been given 3 of these things, I can always find the 4th one. Right? If I'm given A union B and intersect and probability of A, then I can plug those things in and solve for probability of B. Right? I have to be given 3 of them though. Notice that these two things don't really have anything in common, because this doesn't say that B has anything to do with the complement of A. Right? So this is the rule of complementary events. This is the additive rule of probability. Right? So let's go ahead and look at an example. Okay. Hospital records show that 12% of all patients are admitted for surgical treatment. So of all patients that walk into the hospital, 12% end up in surgery. 16% are admitted for obstetrics, which I don't even know exactly what that is. Anybody know what that is? No? And 2% get both. Right? If a new patient is admitted to the hospital, what is the probability that the patient will be admitted for surgery, for obstetrics, or for both? So it's basically asking, what is the union? Right? So consider the following events. A is a patient is admitted to the hospital, receives surgical treatment. So what's P of A? What's the probability of A? If that's what A is defined as. 0.12. Notice I'm making it 0.12 now instead of 12%. It doesn't matter if you write 12% or 0.12. They mean exactly the same thing. Right? What's the probability of B? 0.16. Or 16%. It doesn't matter which one you use. But if you use the percentage, you have to write the percentage symbol. Right? So now we're going to ask the questions. What's the probability of A union B? And what's the probability of A intersect B? We're given another set of information here. Is that the union or the intersection? That's going to be the intersection, right? That's both happening. So I know P of A is 0.12, P of B is 0.16. The probability of A and B happening is what? 0.02. Now I will say that if you do use the percentages, make sure you use the percentages for all of them. Don't call this 12% and this 16% and then call that 0.02. All right, you want to stay in the same unit. Does everybody realize where I got these values from? Does it make sense? What's going on here? Okay. So now it wants to ask, what's the probability of A union B? There is no other way to answer this question other than the additive rule of probability. That is the only way we can do it. Okay? So there's that stuff. Then from the given information, so P of A is 0.12, P of B is 0.16. Probability of A intersect B is 0.02, excuse me. So now that I've been given these three values, I can find the union. The event that a patient admitted to the hospital receives either surgical treatment, obstetrics treatment, or both is union of A and B. The probability of which is given by the additive rule. P of A plus P of B minus the intersection. It's because this 2% is included in both of those, right? So we can only count it once. So the probability of A union B is 0.12 plus 0.16 minus 0.02, which equals 0.26. Right? Thus, 26%, so see how they jump from decimal form straight to percentage? Because this is kind of how we explain it once we get to the real world, right? This 0.26 is kind of statistical speak. Right? So we figure it all out in the statistical world, and then once we want to explain it to the real world, we switch it back to percentages. All right? Thus, 26% of all patients admitted to the hospital will end up in either surgical or obstetrics. Or both, even. From the following information given, it is not possible to list and assign probabilities to all the sample points. Consequently, we cannot proceed through the 5-step process for finding the probability of A union B. Because we can only use the information that's given to us. Right? It didn't give us information about every sample point. It didn't give us information about every patient that was admitted to the hospital. It only told us some information. So we can draw conclusions from this that the percentage of patients that are neither going to end up in surgery or obstetrics is what percentage? Anybody answer that? It's a compliment. It'll be 74%. So 74% of all patients admitted to the hospital will neither get surgery or obstetrics. Okay? And why do I say 74%? Or 0.74? Because of the rule of complements, right? This plus its complement. Now notice I haven't wrote the notation for a complement of a union. It gets a little trickier, all right? Okay. Now we're going to get and define mutually exclusive. Events A and B are mutually exclusive if A intersect B is empty. If they have nothing in common. That is, if A and B have no sample points in common for mutually exclusive events, A intersect B is 0. A way to think about it is parallel lines have nothing in common. Parallel lines are mutually exclusive. Just right out here in front of the theater, right? There's an intersection, right, where two roads cross. They have an intersection. That's where the word intersection comes from. It's where two things cross, right? Where they're in both Highway 70 and, what is that? Avenue O, I think. So if two roads are parallel, they have nothing in common. They're mutually exclusive. They have no intersection. So if I know two events are mutually exclusive, then basically their union is always just the addition of each of the probabilities separately. Because there's nothing to take away, because they don't have anything in common. Right? So that'd be like our mouse pad example, but where the mouse pads aren't touching each other. Those two mouse pads now are mutually exclusive. All right? They have nothing in common. So the probability of the union would be whatever this surface area is, plus the entire surface area here. I don't have to worry about subtracting off the double. Right? Because they don't have anything in common. So mutually exclusive means nothing in common. So that's what I want you to associate in your brain. Because we'll get to another word called independent, which is a little bit different. Okay? Mutually exclusive, nothing in common. And then here's a picture of two things that are mutually exclusive. Just like the two mouse pads. They are not intersecting each other. So the probability of the union is just the probability of A plus the probability of B. Probability of union of two mutually exclusive events is simply probability of A plus probability of B. Notice here they don't have to subtract off the intersection because they're just subtracting 0. So really it is like the additive rule. So essentially you don't even have to worry about this other formula because it is this formula, it's just this thing's 0. Right? So we're not taking anything away. Right? If two events A and B are mutually exclusive, the probability of the union is just the sum of the probability of each of the events. Because the intersection is 0. Now this does not mean A and B are complements of each other. Does that make sense? Because there still could be stuff that happens that doesn't occur in A or in B. If we look at this diagram, there is still space outside of both of the circles. B would be a part of A complement, but it's not the entire A complement. A complement would be everything that's not outside of A. So B would be part of the complement, but it is not the entire complement. Okay? So I want to keep that. Mutually exclusive does not mean complement. This does not say P of A plus P of B is 1. That is not what it says. Okay? Caution. The preceding formula is false if the events are not mutually exclusive. If they do have an intersection, because we have to go ahead and subtract off the intersection. And really, you don't even need to worry about learning another formula. It is still, this formula is exactly the same as this formula, right? It's just the intersection 0. I don't really like the coin toss example that's in this. So what I want to do is jump to a homework problem. I'm going to have you guys work on it, and I'm going to run over and get your tests. So hopefully we can see this. Let's pick a good problem in here. Here we go. This is a good one. I know that's not very big. Let me see if I can snip it out. This snip tool's nice. You guys ever used the snip tool before? It's kind of a lifesaver, especially when you're doing you're creating a presentation. Because you can go to anything online, snip it out, and paste it into a document. Which makes it really nice. And now, see, I can zoom in and we can actually read it. Okay. I want you guys to answer these 3 questions. I'm going to run to the office. I'll be right back in 5 minutes, and then we'll go over these answers. So for this, we don't care about the sample space. We don't need it. So the answer to part A says to find the probability of D complement. So we're going to use this rule, right? We're going to use the rule of complementary events. So the probability of the complement is equal to 1 minus the probability of it happening, right? I can solve this equation for P of AC, which is the same thing as P of DC. Just we call the event D instead of calling it A. So the probability of D complement is going to be equal to 1 minus the probability of D. The probability of it not happening is 100 or 100% or 1 minus the probability of it happening. So 1 minus 0.7, so we got 0.3. Does everybody agree with that? The probability of D complement is 0.3. So let's go in. I'll jump to the homework. Just to put it in. So, type an exact answer in simplified form. 0.3 is simplified. There we go. So we got that one right. So let's find the probability of B complement. The probability of B not happening is equal to 1 minus the probability of B happening, which is equal to 1 minus the chances that B happen is 0.4. B happens. So our answer is 0.6. So if there's a 40% chance of it happening, there's a 60% chance of it not happening. We go in here and put 0.6. Now, when you guys go and do this homework on your own, the numbers are going to change. The method's not going to be any different, but the numbers will change. So now let's find the union. What rule am I going to use to find the union here? What am I going to have to do? Additive rule of probability, right? I'm going to have to use this. So the probability of the union is equal to the probability of each piece minus the probability of the intersection. If I wasn't given this value, and it didn't say that they were mutually exclusive, I couldn't answer that question, because I don't know what they would have had in common. Now, if I wasn't given the intersection and it said they are mutually exclusive, then I would just add together B and D. But I know that they have to have something in common, because what happens when I add together B and D? It's greater than 1, right? So that means they have to have something in common there. Because the probabilities can never be greater than 1, no matter what you add together. So part C, let me go ahead and do it on the next board. So I can write it higher. So part C says the probability of B union D, D, is equal to the probability of B plus the probability of D minus the intersection, right? So it's probability of B plus the probability of D minus their intersection. So that equals the probability of B is 0.4 plus the probability of D is 0.7 minus the intersection, which is 0.2. So our answer here is 0.9. You guys agree with that? There we go. All right. You do have your view and example, ask my instructor, all that help. And I did change this ask my instructor to where emails to my Eastern email, which is better. You got the textbook there to help you. View and example is always nice. This is actually the problem number in the textbook. Chapter 3, Section 4, Question 42. That's what that represents. So if you're having trouble on this, you could go and open up the textbook and pick problems that are around number 42. They're going to be similar to this. Pick the odd numbers because they'll be in the back of the book. And then we finally get in a little bit further. All right? So let me just read this real quick. We won't answer this one, but I want to read it at least. All right, so it says, one institute mandates that for every 100 items scanned through the electronic checkout scanner at a retail store, no more than 2 should have inaccurate prices. So when you go to Walmart and you're scanning your items, really theirs is a lot higher than that, right? Because there's hardly ever an issue with scanning an item. Sometimes it happens. As a matter of fact, I went to Albertsons like 2 weekends ago and bought a 12-pack of beer, and it rang up for $1.98. So I went back to buy another one, and it rang up regular. Dang it. So that was an inaccuracy. But the lady still, she was like, that's fine, I rang it up. So this is bad. I mean, companies don't want this this inaccuracy to happen because it costs them money. That's why they pay people a lot of money to come up with this stuff. Because they'll lose a lot more money from inaccurate checking than they will paying that employee. That's for sure. All right? No more than 2 should have inaccurate price. So that means 1 out of 50. Right? 2 out of 100 is the same as 1 out of 50. 2%. A recent study of the accuracy of checkout scanners at the stores of a certain company showed that 65 company stores investigated, 51 violated the Institute's scanner accuracy standard. That's a lot. 51 out of 65. So what is that as a probability? Let's turn it on. 51 out of 65. So 0.78. 78% of these stores violated that policy. So it's asking if one of the 65 stores is randomly selected. That's very important. It has to be selected at random. I can't go in and pick a store that I know is inaccurate. Right? That biases this. What is the probability that the store does not violate the Institute's scanner accuracy standard? So, does violate is 51 out of 65. So what would I do for does not violate? 1 minus that, right? It's its complement. Or what I could do is 41 or 14 out of 65. Right? Isn't that the same thing? So what's 14 out of 65? 0.22 once you round it up. Or you could do 51 out of 65 and then 1 minus. It's the same thing. So the question says round to 4 decimal places. So it's going to be 0.215 what? Do that in your calculator. 4. 4, it'll get rounded up, right? There you go. So there's a 21% chance that the store will not have inaccurate scanners. That's not very good, right? If I'm the CEO of this company, I need to go investigate these scanners. I mean, you don't want almost 80% of your scanners to not live up to this standard. That's bad, right? They do this kind of stuff with airlines a lot. There's certain things that they have to pass, and I think Southwest is usually at the very top of this list as far as having less manufacturer's defaults or less defaults in general. Part of that is because they own their airplanes, which is different than the other companies. The other companies actually lease their airplanes. So Southwest makes enough money and then they go and buy an airplane. Their business model is a lot more sound than the other companies. That's why they do well and the other companies don't. All right? So there's an example. So this homework assignment covers 3 sections. It covers 3.2, 3.3, and 3.4. 3.2 deals with unions and intersections. 3.3 deals with the additive rule, or the complement rule. And then 3.4 deals with the additive rule. Okay? So this homework assignment is due tomorrow by midnight. Haley does have hours today, right? 3 to 5 in the alley. And there's computers in there, right? Okay. Yeah, so I have this 3.2 to 3.4 section is due 6:17 by midnight. If there's not a time on here, it means by midnight. Okay? So we're moving right along. Okay. You passed back your exams, which were very good, by the way. Class average was almost a B, which is very high for any math test. Anything over a 70 is pretty high for the class average. So I guess I should have made it a little harder, but I didn't want to do that. The test was worth 58 points. All right, so you got correct right out of 58. Go through and count up your number of minuses and make sure I didn't take away too much. Okay, if I took away too much, come and bring it to me and I'll fix it. All right. If I didn't take away enough, well, that's your freebie. All right. 1, 2, and 3 were fine. I don't think anybody missed those. Number 4, there was a little bit of a discrepancy, but that is actually a class relative frequency. 0.5 is the relative frequency. Right? The class frequency would be 25. Number 6 says, which is not a measure of central tendency. I mean, you can go back and read in the chapter, the central tendency chapter, it's mean, median, and mode. So the thing that's not a measure of central tendency is the range. The range is a measure of variability. Number 7 was kind of a difficult question. I was actually just asking for one portion of the normal curve. Look, you can Google normal curve and look what comes up. All this stuff. Right? This isn't something that I just thought up. This is something that's been around for a long time. So what I was actually asking in question 7 was for this portion right here. Because I asked for between 107 and 116 miles an hour. So that's between 1 and 2 standard deviations above the mean. So I was actually asking for this number written in decimal form, which would have been 0.135. And you did have those values on your formula sheet. Right? In your empirical rule, you could have came up with that. So I didn't expect you to memorize that stuff. This is the empirical rule, right? 68, 95, 99.7. All right. Number 8, everybody did well. Number 9 was fine. Really, if there was an issue, it was just probably because of a calculator. It's probably one small error. It wasn't in the understanding, which is more important. Right? You understand how to do it, even though your process might have been a little bit off. Number 10 was good. There was 18 out of 25, or 72% of those data values fell within 1 standard deviation of the mean. Then it went 96, and then 100. So I would say that this data is normally distributed because it fit the empirical rule. It was actually stronger than Chebyshev's rule. A lot stronger. Everybody did good on part D as well, the approximation, range over 4. And number 11 was good. That was, 11A was really the only kind of formula I didn't give you. You had to know that it was QU minus QL. And then I've seen some small issues with B and C that probably dealt with order of operations. What happened there was students probably did QL minus 1.5, hit enter, and then multiplied by IQR. Well, what do you have to do? You have to do the multiplication first, right? And then the subtraction or the addition. And then I had you graph it down at the bottom. Everybody did fine on the graph. All right? By and large, it was really good, though. Number 5 was probably the toughest one on the whole test. Let's go look at question 5. And the reason is because the way that it was written. Right? It was written mean, median, and mode, but the mean is bigger was actually written to the left, and I think that kind of threw students off. Does everybody see that writing it? Because I asked skewed to the right, right? So there's a graph that's skewed to the right. The mean is always pulled towards the skewness. The mean will be somewhere over here. The median will be here. And the mode is always where the peak is. So the answer was written this way. Mean is greater than the median is greater than the mode. But I think if I would have rearranged that, everybody probably would have got this question right. If I would have wrote it this way, the mode is less than the median is less than the mean. Everybody see that those two things are the exact same? And I think if I would have wrote it this way on the test, it kind of would have given it away. Yeah, I think the hard part with this is the mean is farthest to the right, but it's written farthest to the left here. That was kind of the tricky part with that question. But remember, the way the Pac-Man is facing is always the biggest. Remember, the mean is always pulled towards the skewness because the outliers have an influence on the mean. The outliers don't have an influence on the median or the mode. All right? And I can even let's Google skewed to the right. There you go. Mean is always pulled.